So this is the Amtrak dataset, and we need these libraries as usual. We have the Amtrak data, we change them to Sybil, we plot the Amtrak dataset, and we know that we have a curvy U-shape pattern, so trend actually, and we have seasonality. So that's why we know how to capture these two using the regression. The regression does not assume a stationary data set, so that's why we are able to capture these using the regression, linear regression model, quadratic in this case. So before we do anything now, let's just look at the beginning. Actually, I would like to look at the autocorrelation before we do anything. Just I want to say something about the data. If the data is not stationary, some of the things that we do, if you remember, we talked about differencing to stabilize the mean, and we can do transformation that helps to stabilizing the variance. But now let's look at the autocorrelation. And as we said, the autocorrelation is the correlation between values of a time series in the neighboring periods. Why it's called auto, by the way? Because it's a relationship between the series and itself, okay? So we are going to look at ACF1, ACF2, which is lag 1 autocorrelation, lag 2, etc. So to do that, I would check the autocorrelation. So first, let's check autocorrelation. And actually, I would like to say something, because the idea is we would like to know something about the random walk. Is it a random walk or no? So, right. So to say something about random walk or no, we have to look at the autocorrelation. We have to check two methods. Not we have to, but there are two methods that we can check. We look at the ACF plot of the ridership and its lagged values. Or the method number 2, we check the ACF plot of the first difference series. So using one of these methods, we can look at whether we have a random walk or no. So let's do method 1, which is ACF plot of ridership and its lagged values, right? So to do that, we're just going to find ACF for the Amtrak time series. Let me look at lag max. Let me get 36 lags, and let's do auto plot. Could not find the function ACF. Do you have feast? So let me add library feast. So now, after fixing this by adding the library and feast, we can get the graph that we're looking for. So what do we have here? We have a very strong positive autocorrelation at lag 1, because look at them. All of them are actually above the blue limits. And the correlation declines slowly, but still remains positive. It has a repeating behavior and repeating spikes at 12, 24, 36. So we have seasonal multiples. So that tells you that, hey, this doesn't seem to be, or we have an autocorrelation. Also, we can look at the other method, which is method 2. We can look at the ACF, the autocorrelation function plot of the first difference, which is lag 1 series. So this is lag 1 series, which is finding the difference, right, between the ridership and the previous values. Just one difference. Okay. After that, we are going to plot the ACF. So what can we do? We can do Amtrak. Then let's mutate diff1. Mutate the difference ridership 1. So we are going to find the first difference. So if you mutate this, mutate difference equals ridership. So if you find this, we are going to get the difference column. We added the difference columns that find the difference between yt minus 1. So just subtracting this minus this, and then this minus that, and so on. So it gives you these differences. Also, to just get the ACF, we can we can filter out the NAs, the first one, so we are able to immediately draw the ACF plot. So I can excluding exclamation mark the NAs of the difference one. So I'm excluding the NA. I'm excluding just the first observation. After I'm excluding the first observation, what I'm going to do, I'm going to plot or to get the values of the IFF1. After that, I'm going to plot these. If you just get ACF, you are going to get the table of these values. If you continue, you are going to get the the plot of these. So this is exactly what we've seen in the slides, and it's clear that the series is not a random walk. We have some predictable structure left. The differencing successfully removed most of the trend, as it's clear that we didn't have a trend. We didn't have that slow decay from the previous ACFs. However, we still have some seasonal autocorrelation remains. So we do have some seasonality here. We can actually add more lag max 36. Yeah, we can see that this is, we have a seasonality. If we do another seasonal differencing at lag 12, then we may get rid of this, but this is not the goal of just we want to show that this is not a random walk as we explained before. So after that, let's now do modeling. So the first thing to do is we are going to partition the data as we did before. So we can look at the training data to be from the Amtrak, filter based on the index. Our index is the months, remember? I'm going to keep everything up to 2001 April or March. This is going to be my training data. My validation, again, Amtrak, pass it to the filter index. I'm going to get from 2001 April up to end of the data set. Let's run. I have 123 observations. We have two variables, the index month and the ridership. Validation, we have 36. We have months and the index months and the ridership. So after partitioning, we are going again now to model our original data. So we want to capture the trend and seasonality using the regression. And we did this before. The problem is not with the first step. The problem is going to start, our new job is going to start from step number 2, which is after modeling on the training. So model on the training data. So as I said, we model so to capture the trend and seasonality using regression. Using linear regression, right? Linear regression. So this is what was done before. So train the model. So we want to train the model. I'm going to call it train linear model. We can add a trend and seasonality. Season training. So I want to go to training data set. Then I'm going to develop model. My model is going to be TSL, right? Time series linear model. Ridership is my response variable. Then I'm going to have trend plus the square of the trend plus the season. So actually, if we do that, season, I forgot these guys. Okay. So this is a list. Let me go get this up a little bit. So let's look at fitted, train, linear model, trend, and season. Actually, I don't like trend. Let me run again. To be honest, I want to delete all of this and start scratch. So let me run this. After that, running ACF, I don't want it. I don't want this. The training again. Then this guy. Okay, here we go. Then let's do the fitted train.lm trend season. Okay, this is my time series right now. I have the model, I have the month, I have the fitted values. the fitted values, not the actual, the fitted, using our model, the one that we have just built, right? Now, okay, this is my fitted values, right? These are my fitted values. And actually, I don't want, let me just type it here, fitted train.lm season. So I don't want the fitted actually, because the next step is going to be build autoregression on the residuals, right? Because we have leftovers. We want to check the first of all, we want to check the autocorrelation of the residuals. So if the residuals are autocorrelated, so it means the model errors are not random. So the residuals are not random. And that means they are related to each other. They are not independent, right? To do that, first of all, I would like to do the following. I would like to look at the residuals, then we plot them, okay? So I would first keep that model, but I would like to create train.lm.trend.season.reset. So this is the one that I care about. I'm going to pick the residuals only. So I'm going to go to my train LM trend season. I'm going to go to this data set, and I am going to go to the training data again, right? And I am going to, let me try to do that. Let me just go to train LM season. I would like to go to residuals. Let me look. So now this gives me the residuals. If you click on this, we have the model, we have the month, we have the residuals, which is the error, which is the difference between the actual data of January 1991 and the fitted value. The same thing for February 1991, and so on. So these are the residuals, the difference between actual and fitted values. And I would like just to take off this model column. And it's annoying. Just I want to take it off. So I want to select this, deselect this out. So I'm going to minus the model. Deselected. It's dot model because the name is dot model. Look at this dot model. So I'm going to take it off. So if I look at this now, I have a new data set now. I have the month, I have the residuals. Because remember, when we build the autoregressive, we're going to build this on the residuals, right? So we want to check first the ACF of the residuals. And the question is going to be, did my model capture all of the time-based structure, or still we have memory hiding in these errors? So look at ACF, autocorrelations of residuals, okay? The autocorrelations of residuals. It's going to be ACF, train, just the residuals, lag max, let's get 36 again. After getting the table of ACF, you can, by the way, run this code without the auto plot. You are going to have a table. But I want to see this, okay? I want to see this. So if you run this, this gives you the autocorrelation function of the residuals. Okay, we have a strong lag 1 correlation, but this decays very fast. It decays to 0. And this is a classic stationary autocorrelated pattern. It's not a trend. Because if it's not stationary, the data is going to be near 1. They're going to, or the decay is going to be very slow. Okay? So we do have a stationary data set now for the residuals. Why I have to confirm this? Because actually to do the autoregressive on the residuals, you have to make sure that your data is kind of close to be stationary, and this is stationary data. Most of them are inside the black, the blue lines. Number one. Number two, the decaying is very fast. Okay. So now we are going to look at the AR one. Remember, let me just type something for you. Autoregressive. So auto now okay, let me say something. The plot has a strong lag 1 correlation, but it decays fast. So the residuals are stationary. Okay. Now, so we can build AR1 on the residuals. Okay, and the residuals. So let's build AR1. AR1 is enough. Can we do AR2? No, there is no need to do AR2 because we have, okay, we have just spikes here. First 3 lags. So it's enough to do AR1 on the residuals. We will be capturing these correlations, and that's it. So let's do AR1. Let me just remind you, what is AR1? What is AR1? What AR1? What is F order 1? Autoregressive of order 1. The equation of autoregressive order 1 is going to be the error. We are modeling the error. Remember, the error is going to be equal to the beta naught plus beta 1 times the previous error plus what is left over, epsilon t. So beta naught is going to be the intercept. Beta 1 is the autoregressive coefficient, which is, it asks this simple question: how strongly today's residual depends on the last one. And this is the new shock, or the new random shock at time t, which is the white noise. So to build the auto regressive of order 1, we have to do the following. So we are going to build this one. Again, we have still training data. It's a 2-layer models. The first layer on the training data set was the regression, linear regression. Then we found the residuals. Now we are building the ARIMA, the autoregressive, which is technically ARIMA, the autoregressive of order 1 on the residuals. So what I'm going to do, I'm going to call it train dot residual. So we know that we build this on the residual. I'm going to call it AR or ARIMA. Okay. So what data I'm going to look at? I'm going to look at my residual data. This is my data now. This is my new data. Okay. So it's going to be train.lm residual. And I'm going to model again. The function name is ARIMA. So ARIMA, let me go back and look at this guy. My response function is reside or residual .rez. And I'm going to do something here. I'm going to say 1 plus PDQ. PDQ 1, 0, 0. What does this mean? First of all, this is my response variable, which is ET equals tilde, beta naught, which is 1, plus PDQ 1, 0, 0. 1, 0, 0, the 1, that means we are doing autoregressive of order 1. So this is the value. Let me write this. So P equals 1. So, okay, the first value belongs to P. The second value belongs to D, difference. The last value belongs to Q. Okay. So P is equal to 1. That means we do AR1. Okay. AR1. The second part, which is the value of D, which is based on the difference. Right? The difference here is equal to 0. That means no difference. So the difference is 0. D is equal to 0. So we did no difference here. We do not do any, we don't want to do any difference in the data set. Why is that? I'm not willing to do any differencing, because the data is already stationary. We've seen that it's stationary since the residuals are stationary already. If they're not stationary, we have to do that. First difference or 12 difference, etc. Depends on what kind of difference it depends on the data set. It depends on what kind of residuals we have. And the last part, which is a Q, and we're going to speak about this later. Q is 0, it's moving average. So no moving average term yet. And we will be covering this in the next lecture. Okay? So this model means we are doing AR1. What if you're doing AR2? You just change this one from 1 to 2. 3. There's going to be 3. If you add differencing, you add 1, and so on. So right now we are just building the ARIMA. So let's look at the ARIMA. Now, what if you look at the fitted values of AR1? Let's look at the fitted values. You can look at just fitted of what? Of the train residual ARIMA, or these are the fitted values. So these are the fitted values. And remember, we have actual values are these, and these are the fitted values, right? Now, let's plot the actual residuals and the fitted residuals and see the differences. So let's plot the actual and fitted residuals just to look at how much we are fitting on the training data set. So train.l, we look at the residual. I'm going to add autoplot. So this is our residuals. I'm going to add another layer. I'm going to take my data from the fitted. Which one I'm looking for? Train, this one. Train, yeah, I have to add fitted here, right? Because we need to look at the fitted. Yes, we look at the fitted value. Then I'm going to, aesthetic is going to be, y is going to be dot fitted, color equals red, right? So these are the residuals, the actual residuals and the fitted residuals. And it seems that it fits the residual really well. Good. We are fitting the residuals really good, right? So now we are going to look at the new residuals after fitting the AR model, which is the residual of the residuals. Residuals of the residuals. So let's look at the new residuals after fitting the AR1. So we are going to go to ASF, and I'm going to look at my residual autoregressive. I'm going to look at not only the train, I'm going to look at the residual of this. So the residual. So hold on. Residuals of the train res dot AR. Lag max, I'm going to have 36 again. And I'm going to graph this autoplot. So this is what we have. We have all of the black bars really well inside the blue dashed limits. So we have no statistical significant autocorrelation left, no autocorrelation. All of the spikes, all of them randomly like wiggling around the 0. No consistent pattern. We don't have any pattern here. The residuals of the residuals are white noise, and we don't have a lag one like clear or something. So the AR1, so what is the result? I mean, what does this mean? It means that the AR1, autoregressive 1, did the good job. The regression that we did on the residuals actually did well. First of all, the linear regression, the first layer handled the trend and seasonality, and the AR1 cleaned the leftover autocorrelation. So This is what we can tell. This is what we can say. So all of the black bars are inside the blue dashed lines. So no statistically significant auto correlation lift, right? AR1, we can say AR1 cleaned the lift over autocorrelation. So this is what we have done. We can look at the report. We can report what we got. So report, we use report, train.trace AR, and this is what we have shown in the slides. Look at AR1. This is the constant term. This is beta note. Let me write this down, by the way. So the error is equal to beta note. What is beta note? 1492 plus y negative. There's no negative. Plus beta 1. This is beta 1. This is the coefficient. This is slope, which is 0.5998 times E of the previous error. So this is my equation, right? By the way, these are the estimates. So these are ET hat, etc. So these are the estimates. So this is our AR1 equation. We can do forecasting. So now let's do forecast. These are the values of AIC, ICC, BIC. So let's look at the forecast. Let's do forecast, just one value. Let's do a forecast. Forecast. So we just forecasted one residual of April 2001, which is 7.4. 7.4. So let's look at the residual from the look at, and I'm going to speak about this in a second. Look at the residual from trend.lm, trend season reset. So let's go to this guy, trend.residual. Let's filter, look at just one piece. Month, year month, in this case, year month is what? 2011 March equals. So this is the residual of the original data set in 2001, March 2001, right? Which is 2.1. Now, if I actually go to this equation, if I'm looking for the error of what's so called April 2001, it's going to be this beta note plus beta 1 times the error of March 2001. So technically, if I actually do that, if I just plug in the whole thing, if I say ET1, let me just copy this. So if I do this, if I just plug in 0.1492 plus 0.5998 times 12.1075, it's going to be equal to 7. What's the value? 7.4. 7.4. So this is the forecasted value of April using the autoregressive model that we have built. We have the residuals of the previous months, so we can forecast the next months. So now, what does this mean, 7.4? So this is computed directly using the forecast function, as you see now, and it's positive. So it's positive means the residual is positive. So let's understand, what does this mean? 7.4. The residual of April 2001 is positive. That means if you subtract the actual riders, the actual number of riders minus the forecasted number of riders For April 2001, the answer is going to be positive 7.4, which is 7,411. So in other words, the regression model is going to produce ridership that is too low, and that we should adjust it by adding 7,411 riders, right? So if you look at the validation set, what we have done, if we just look at the if we just want to look at the riderships, let's look at the number of the riderships. Let's go back to the let's look at the riderships. Let's go to train LM trend season, not the residuals. Just let's look at number of the riderships. Let's first look at let's do forecast using the original model, just the original model, okay? Without looking at the AR one. So H equals 1. So we are forecasting April 2001, number of riders. So we got 2004.27, which is actually 2,004,271. So this is the forecasted value of April 2001 on the validation set, just one forecast, just one, okay, using our first model. So let me compare to what is the actual value. Actual value. Just go to Autoregressive, look at the actual value. Very simple. Let's go to Autoregressive and filter month equals year, month, year, month. Let's look at 2001 April. So the actual value is about 2 million, right? And 23,792. So let me write this down. So the actual number of riders is 2,023,792 riders. The forecast, this is okay, we're speaking about in April 2001. The forecasted value using our linear regression model, actually it's non-linear, is what we got? It's 2,004,271 riders. Forecasted number of riders, right? So what we have done, we can say we can improve this forecasted number. So we improved this forecasted number by adding another layer, which is AR1, right? By increasing this number by what? Remember what we got here, 7,400 by 7,411 riders. So the new forecast using the two layers is the old one plus the 7,401, which is going to be, so this is 11. So this is 200, actually 10, then 11, then we have 682, I guess, riders, which is a closer. This is closer and improved forecast. One more time. So we did a forecasting using the second model for April 2001. We found that the forecasted value is 7,411, and we come up this one from the equation. Just we plug in the actual value, the actual error, the previous error. We get 7,400. That means we can adjust the forecasted value by 7,400 drivers, we can add it because it's positive. We can add. Actually, if it's negative, we have to add it because it's going to be. We are going to reduce that number, the previously forecasted number. So we add this error because it tells us that we have to add this to improve the forecasted number. So this is the error that we would add to our previous forecast using the regression. So this is using the regression. So this is mostly everything that I want to speak today. And we can look at the accuracy, but this is going to be something maybe we're going to do later. But this is enough for now. And so in this video, we built a autoregression 2-layer models using the original model and AR1 to improve the forecasts of the future values.